let's get into First Principles Daily, episode 19. It's June 24th, 2026. Today we reason from raw materials, not analogy. A commercial kitchen build-out can run $500,000, yet the raw steel, compressors, and ductwork inside point to a far lower floor. A typical restaurant kitchen build-out lands between $300,000 and $600,000 before the first plate leaves the pass. The dominant materials remain sheet stainless, copper pipe, refrigeration compressors, and galvanized duct. All of those materials trade on commodity markets at prices measured in dollars per kilogram. The gap between those material values and the final invoice is large enough to treat the entire category as an open engineering problem rather than an immutable cost of doing business. Most commercial kitchens are still assembled the way they were 30 years ago. An architect draws a custom layout, a general contractor sequences a dozen separate trades. Each trade prices its work against the risk of working inside an existing building shell. Health department plan review, fire suppression certification, and electrical load calculations all restart for every address. The same stainless steel table that appears in dozens of restaurants must be fabricated and inspected as if it were unique. Plumbing and electrical rough-ins arrive on site as loose pipe and conduit rather than pre-terminated modules. That approach multiplies both labor hours and the chance of a later change order. Equipment dealers quote list prices that already embed 2 or 3 layers of margin. Those list prices rarely move even when the underlying commodity costs fall. The result is a finished price that feels normal inside the industry. Every participant has optimized for the next step in the existing sequence rather than for the physics of preparing food. Square foot costs of $300 to $600 therefore persist across independent restaurants. The same square footage inside a quick service chain or ghost kitchen operator can be finished for noticeably less once the layout and utility runs are frozen into repeatable modules. One reason the pattern endures is that each new project carries the accumulated risk of prior failures. Leaks discovered after drywall, hoods that fail smoke tests, or compressors that trip breakers under actual load all add up. Every contractor adds contingency for the unknown interfaces that only appear once the walls are open. Another factor is the financing layer. The operator pays carrying costs on the lease while the build drags through sequential approvals. Those weeks of idle rent are folded into the capital budget as if they were an unavoidable material expense. The same logic applies to change orders. When a health inspector requires an extra hand sink or a fire marshal demands a different damper location, the cost of ripping out and rerunning pipe is passed straight through. No one earlier in the chain held a performance specification that could have prevented the conflict. A rough magic wand estimate begins with the major material categories. A 1,000 square foot kitchen might contain on the order of 2,000 to 3,000 kilograms of 304 stainless sheet and tube. Another 800 to 1,200 kilograms of galvanized duct go into the exhaust system. 4 to 6 commercial refrigeration compressors add perhaps 400 kilograms of steel, copper, and aluminum combined. Insulation, wiring, and fixtures contribute another few hundred kilograms of commodity value. At current mill prices for stainless and copper, the entire raw material stack sits somewhere between $8,000 and $15,000 before any forming, welding, or certification. Adding a generous allowance for fasteners, gaskets, and minor electronics still leaves the floor well below $25,000. Against a finished build-out price of $400,000, that produces an idiot index on the order of 16 to 20. The index does not claim that $25,000 is an achievable selling price. It simply flags that the dominant cost is not the atoms themselves. The largest single slice of the gap sits in the repeated custom engineering and sequential on-site labor required to satisfy fragmented code jurisdictions. Each jurisdiction's plan review cycle adds weeks of carrying cost and redesign iterations that have no counterpart in a factory setting. A second large slice lives in the dealer to contractor markup chain. That chain compounds because equipment is still sold as individual SKUs rather than as tested utility modules. A third slice appears in the mismatch between one-off layouts and the actual thermal and airflow requirements of cooking equipment. Every hood, walk-in, and prep table is sized and ducted from scratch, instead of being drawn from a library of pre-approved assemblies. These three categories, regulatory repetition, fragmented procurement, and non-standard interfaces, account for the bulk of the observed index without invoking exotic materials or hidden physics. One objection sometimes raised is that the finished price also buys liability protection and code compliance. Yet those protections are themselves produced by repeated engineering effort that could be amortized once rather than recreated each time. Another objection notes that on-site conditions vary. The variation is often smaller than the custom work implies. Most restaurants still need the same basic zones for hot prep, cold storage, warewashing, and exhaust. The differences are mainly in how those zones connect to the building's existing columns and drains. A redesign would begin by freezing a small number of utility core modules. Those modules would already contain hood, fire suppression, makeup air, and electrical distribution in a single tested package. Once those cores carry third-party listings that multiple jurisdictions accept, the plan review cycle collapses from months to days. The second move would standardize the remaining floor plan into 2 or 3 repeatable footprints. Those footprints would be sized around common equipment footprints rather than around the quirks of each tenant space. With those footprints fixed, stainless tables, refrigeration racks, and plumbing trees could be pre-cut and pre-wired in a factory setting. That shift would cut on-site labor by roughly half. The third move would shift procurement from dealer list prices to direct volume contracts for the standardized modules. Direct contracts remove 2 layers of margin and let the supplier amortize certification costs across hundreds of units. Each of these steps requires a different enabling condition. Code authorities would need to accept performance-based listings rather than prescriptive drawings. Manufacturers would need to invest in UL-style testing of the integrated core. Operators would need to accept a constrained set of layouts in exchange for lower capital cost. The genuinely hard constraints are the real safety requirements around fire and refrigeration. No redesign can eliminate the need for listed suppression systems or reliable temperature control. Jurisdictional fragmentation remains the largest policy obstacle. Even a technically superior module still faces dozens of separate approval processes until a critical mass of cities agree to reciprocal acceptance. A further practical limit appears in the interaction between the kitchen and the building shell itself. Existing grease traps, gas line capacities, and structural penetrations still differ enough that some field adaptation will remain necessary. That adaptation can be reduced to a handful of standard transition kits rather than full custom engineering. One principle is that every repeated regulatory review is itself a manufactured part whose cost can be driven down by pre-certification. That process works exactly as the restaurant's stainless tables could be pre-certified. A second principle is that interfaces between trades, hood to duct, compressor to electrical, carry hidden coordination tax. That tax only disappears when those interfaces are frozen inside a single tested assembly. The question now is, which city or chain will first publish the test data that lets the next operator order a kitchen the way a factory orders a machine tool? That's a wrap on today's first principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove